Energy conservation. All right, so in regards to the ball being placed on a ramp and how high will it go up on the other side, that depends upon where is the ball released onto the ramp. So for example, if you have a kind of a basic U-shaped ramp like so, and you release it from this elevation here, then what's going to happen, as long as you don't shove it and you just let go of it, the ball will start off initially at rest. It will begin to speed up, and then when it reaches the very bottom, it's going to be moving at its maximum velocity. And then as it moves up on the other side, it's going to start slowing down. And if there's no dissipative forces, in other words, if there is no friction, no sound, no heat, nothing being generated here, then in theory, that ball should arrive on the other side at the same elevation where it was released. Now, because of the dissipative forces, that never will happen. It will go up, it will get close to it, and it'll fall a little bit short, and then next time it'll be a little bit short, and next time it'll be a little bit short until finally it comes to the rest of the bottom. But if there weren't any type of dissipative energy, then the ball would arrive at the other side at the same elevation. Even if you were to have something kind of like this here, where you have maybe a steep side on one side, and then all of a sudden it becomes gradual on the other side. So if this was the situation, let's say if you released it from this elevation here, then the ball will speed up. It will slow down, but it will slow down a little bit more gradually, but will still only arrive at the same elevation where it was released. Now let's say you have something a little bit more unique. Let's say you release it from here, and say maybe like a small hill, a really big hill, another kind of medium hill, and then moves on. And if I release it from, let's say, at this location here, then what's going to happen is that this ball cannot go anywhere above that line. So that means the ball will go down through here, goes over this little hump, will come back up, and will only stop here. It will never be able to complete the rest of this path here. So all of this will not be able to be completed. It will only stay in between this area right here. So with the, so the amount of energy you have at the very beginning will always equal the amount of energy you have at the end of the system here, ignoring any type of dissipative energy occurring. Now, as this diagram shows here, someone is jumping off of a platform, and in this case, diving into a bucket of water, we hope. And so just kind of reflecting upon the energy of the system here. So let me back up just a little bit. Is that the total energy of a system is going to remain the same. So the conservation of energy here, that energy cannot be created or destroyed, but you can change it from one form to the other one. Which means that, so if you look at potential energy and kinetic energy, potential energy has to do with the position of the object. Kinetic energy has to do with the motion of the object. Let's pretend this is 100 meters above the ground. And down here at the bottom will be 0 meters, and halfway will be 50 meters. And then in between here, we will have 25 meters and 75 meters. Now, the actual heights really don't matter. I'm just picking something as a reference. So, and then we have, let's say, pretend that we're dropping a ball from 100 meters. And we want to know what's happening to the potential and kinetic energy as it's falling down. So, we'll be looking at what is the potential energy. We'll be looking at the kinetic energy. And then also the total energy. I'll put E sub E to represent the total energy. Now the key thing to remember here is that the total energy is equal to the potential energy plus the kinetic energy. So the sum of these two will always equal this. So let's say we look at for potential energy. Potential energy I'll just write down here, potential energy is equal to mass times gravity times height. And so let's say we took the mass of this ball and gravity, which is going to have a value of 9.8 meters per second squared. Now make sure it's meters per second squared, not meters per second. And with this height, and let's say when I multiply these three values together, we end up getting a value of 10,000 joules. Capital J for joules. Now, when you first drop the ball does not have any velocity. And so, one thing about kinetic energy is equal to 1/2 mv squared. And so, since the ball is not moving at that point in time, it's not going to have any kinetic energy. So over here, it's going to have 0 joules of energy. So the total energy is a sum of these two values combined together. So the total energy of the system will be 10,000 joules. Now, once you found the total energy of the system, this is a constant. This is going to remain the same all the way down. That means once at 75 meters, the total energy of the sum of those two will still be 10,000 joules. And once at 50 meters, it's still going to be 10,000 joules. Once at 25 meters, it's going to be 10,000 joules. When it reaches the ground, it's still going to be 10,000 joules. So that is something that's going to be helpful in if you ever had to solve for either one of these two. Is that once you find the energy of the energy of that system remains constant. So as it begins to fall down, and let's say when it's at 75 meters above the ground, the height is not nearly as great. And so because the height is going to be smaller, the potential energy is also going to be smaller as well. And so let's say when it reaches at this point here, it's going to be 7,500 joules. Again, I'm just kind of making this number up here. Now, since the sum of these two have to equal 10,000 joules, it's pretty easy to figure out how would you go about finding out the kinetic energy. Now, if you subtract these two, you'll get the amount of kinetic energy that the ball would have. It would have 2,500 joules of energy. You have to keep in mind when the ball is being dropped, when it reaches this point here, it's going to have just a little bit of velocity to this. So it has a small velocity at that point. So because of that, as it's falling down, the velocity is going to be increasing. As kinetic energy is also going to be increasing. So it begins to descend down and it gets to this point. The ball is now going to be traveling at an even higher velocity. So the velocity is going to get bigger. So what's going to happen to the kinetic energy? Well, the kinetic energy is going to be getting larger. So let's say at halfway, it should have half the kinetic energy. So it would be at 5,000 joules. Well, then how much potential energy would it have? Well, again, the sum of these two has to equal 10,000. It will have also 5,000 joules. So at the midpoint of its descent, the amount of potential energy and kinetic energy are always going to be equal to each other. And that's one kind of an important thing to remember here, is that when an object is falling at its halfway point, the potential energy and the kinetic energy are going to be equal to each other. Then, as it begins to descend down, its height, its elevation is going to be getting less, which also means its potential energy is going to be getting less. So down here, we're going to start getting to about 2,500 joules. Well then, to find out how much kinetic energy you're going to have, you just subtract these two values, which will then come out to 7,500 joules. And then when it reaches this point here, when the height isn't nearly as great, but it's going to be going even faster. So its velocity is going to get even bigger. And then when it hits the ground, or technically it's when something hits the ground here, don't assume that it's going to come to a stop. It's always the moment before it hits the ground. So when it hits the ground, the height is going to be 0, which, if you look at this equation here, if height is 0, the potential energy is going to be 0. So this is going to have 0 joules of energy. But then, how much kinetic energy will it have? Well, the sum of these two has to equal 10,000. So the kinetic energy is going to be 10,000 joules. Now make sure when you're doing these, you're always putting down the units. So the fact that it has all this energy here, that means the moment before it hits the ground, this is now going at its maximum velocity, and the velocity is going to be huge on that. Now, a few things, hopefully, you can see taking place here. Again, the total energy of the system remains constant. Now, a couple other things you should notice here too is, first of all, as you're going down, the sum of these two will always equal the total energy. But another thing too is this. If you notice at the very top, the potential energy was 10,000. But when it reaches the very bottom, the kinetic energy is 10,000. And as it falls down, it becomes 7,500. And here, it's also 7,500. At the halfway point, they're both equal. And then they both have 25, and they both have 0. So they're kind of almost like mirror images of each other, kind of flipped upside down in comparison to each other here. So in other words, when an object is falling down, the potential energy is high, its kinetic energy is low. And as it begins to descend down, those two will flip places here, where this one will become 0 and the kinetic energy will become greater. So all they're doing here is they're basically switching places. So this is going to be kind of important when we start doing some of the calculations. And if you know the potential energy or the kinetic energy of the object, and using these equations down here, we can also find out how fast is the object going, and even how high is the object. So you'll need your calculators here pretty soon. And let's move on to the next part. So let's try a few problems here, and then later on you're going to be doing some problems on your own. A 60 kilogram pole vaulter is running 10 meters per second. How high could they vault? All right, so for this next problem, we're dealing with a person who has a mass of 60 kilograms. They're running at 10 meters per second. And the question is, how high can they pole vault? And this is something that's used quite a bit in sports science, and in helping the athlete to train. By increasing their velocity, they can help determine how high can someone go up. So the ability to be able to pole vault, not only does it take proper form, but also one of the biggest things is how fast can they go? Because the faster you can go, the higher you're capable of pole vaulting. Now, when you're running, you have kinetic energy. And when you're pole vaulting, you're converting all that kinetic energy into potential energy. Because here you're moving, and you're trying to move all that energy and move it into, and bring it up to a higher elevation, where you're not moving, but you're trying to convert all that energy into height, which is going to be due to the potential energy. So you're trying to convert kinetic energy into potential energy. Well, kinetic energy is equal to 1/2 mv squared. Potential energy is equal to mass times gravity times height. But the thing about these two are equal to each other. And so this goes back to rearranging those equations, where since kinetic energy is equal to potential energy, and kinetic energy is equal to 1/2 mv squared, and potential energy is equal to mass times gravity times height. And one thing, if you remember, the masses cancels out, which actually means the mass of this individual does not matter. So whether it's someone who was 60 kilograms or 100 kilograms or 50 kilograms, as long as they're going 10 meters per second and they have good form, they'll all arrive to the same height. It's based upon the physics of converting the kinetic energy into potential energy. So what we need to do is we need to rearrange this equation so that we have 1/2 b squared is equal to gh. And we're trying to solve for how high can the person jump up or pole vault. So basically we had to divide both sides by g. Get rid of the g over on this side here. So we end up with the height is equal to 1/2 b squared all over g. Now, you can either write it this way, or I kind of prefer writing it out this way here, where this would also be the same thing as being b squared all over 2g. So you could either use either one of these two equations here, whichever one you prefer. Okay, so let's plug in the values here. Well, the mass of the person, if you remember, the mass cancels out. So the mass of the person here does not matter. We have the velocity of the person is 10 meters per second. So I'm going to put down over here. So the mass was 60 kilograms, which really isn't needed here. We have the velocity of the person is 10 meters per second. And the other thing is gravity is 9.8 meters per second squared. And so from all this, we're trying to determine what is the height. So plugging in these values into this equation here, I'm going to plug it into this top one up here. So height is equal to 1/2 b squared, so it's 10 meters per second, and I need to square that. All divided by g, which is 9.8 meters per second squared. Now when you're doing this, make sure you put the units in here. So the height is equal to, well, 10 squared is 100, and you're going to take half of that. So that's going to be 500. Now the units for that becomes meters squared per second squared, all over 9.8 meters per second squared. Now, if I take 500 and I divide it by 9.8, I get a height of 51, just basically 51 here. 51, and the units for that would be meters. And the reason why, second squares will cancel out, and one of the meters will cancel out. So you're left with this 1 meter right here. So the height that this person would be able to pole vault would be a very impressive 51 meters. Now, this is not based upon reality, but this is just an exercise of doing the calculations. So an object traveling 10 meters per second will be able to travel a height of 51 meters. All right, let's move on to the next one. The top thrill dragster at Cedar Point reaches a top speed of 210 miles per hour, which is 94 meters per second. What is the maximum height the ride can travel? Okay, the next problem dealing with the top thrill dragster. I actually just looked this up here and just realized that there was a mistake in this problem. The top thrill dragster does not go 210 miles per hour. It goes about half that speed. But still, let's just go ahead and work with what we have here. Even if you were to use the correct speed of the top thrill dragster, yet the height it would come up to would be very close to the actual height of the top thrill dragster. But let's pretend we end up modifying the top thrill dragster so it does go 210 miles per hour, which would be really awesome. So all we're doing here, again with the top thrill dragster, is that it starts off having kinetic energy. And all we're doing is converting the kinetic energy into potential energy. So here it has all kinetic energy. And then eventually it's going to reach up here towards the top at a certain height where it's going to be all potential energy. So the kinetic energy is equal to the potential energy. So once again, we have the velocity is 94 meters per second. We're assuming this is taking place on Earth, so gravity is going to be 9.8 meters per second squared. And we're trying to solve for how high will this travel. So potential energy is equal to kinetic energy. Potential energy is mgh is equal to kinetic energy, which is 1/2 mv squared. Now, the masses are going to cancel out. So just to simplify it, gh is equal to 1/2 v squared. And we're trying to solve for how high would this roller coaster go. We'll call this Top Thrill Dragster Extreme. So we're trying to solve for the height. Height would equal to, we want to divide out g on both sides. So g is over here, will cancel out. So it's equal to 1/2 v squared all over g. So let's plug in the numbers. It's equal to 1/2 the velocity, which is 94 meters per second. And you need to square that, divided by g, which is 9.8 meters per second squared. So let's do this first. Take 94 squared. So I'm going to take 94 and square that. So I get 8,836. I want to divide that by 2 or multiply by 0.5. So divide it by 2. And I get 4,418. And then I need to divide it by 9.8. So divide it by 9.8. And I get a value of 450 point, let's say 82. And the units for that here, meters per second will become meters squared per second squared, all over meters per second squared. So the second squared will cancel out, and one of the meters will cancel out. So it leaves you with the unit meters, which is the unit for height. So if this Top Thrill Dragster could actually go 210 miles per hour, which is 94 meters per second, then in theory it should go to a height of 450.82 meters. For the third problem, a 60-kilogram diver jumps off of a 10-meter diving platform. What is their potential energy at the top? What is their kinetic energy at the bottom? How fast are they traveling when they hit the water? All right, for this third problem, there are a few things that we're going to be solving for, one after the other one. So we have a diver who has a mass of 60 kilograms, and they are 10 meters, so right up here. They have a mass of 60 kilograms. They're 10 meters above the water. So we're looking for what is the potential energy. Now the potential energy has to do with their position. So that would be up here at the top. As they're falling down, all that potential energy is going to be converted into kinetic energy. So when it reaches the water down below, we're looking for what is their kinetic energy right before it hit the water. And then also, how fast, what is their velocity when they hit the water. So we're trying to solve for the velocity. We want to know what is their kinetic energy and what is their potential energy. Now, let's list all the given information here. So we have the mass. So let's list the givens. The mass of the individual is 60 kilograms. The height is 10 meters. Assuming this is taking place on Earth, so gravity is 9.8 meters per second squared. and we're trying to determine what is the potential energy, what is the kinetic energy, and what is the velocity when they reach the bottom. Okay, so the first thing we can determine here is when they're up here at the top, they have all potential energy. So for part A, we're trying to determine the potential energy. Well, potential energy is equal to mass times gravity times height. So to determine the potential energy, we're going to take the person's mass, which is 60 kilograms, gravity, which is 9.8 meters per second squared. Now when you're doing this, make sure you put the units in here, kilograms, meters over second squared, and then the height is 10 meters. So we'll multiply these three values together. So the potential energy is going to be 60 times 9.8 times 10. And we end up getting a value of 5,880. Now the units becomes kilograms, and then the meters per second squared times meter actually becomes meters squared per second squared. And the units for that here will become joules. So the amount of potential energy it has up here at the top is 5,880 joules. I'm going to go ahead and just label this diagram up here. 5,880 joules of energy is up here at the very top. Now, if you remember a little bit ago in the notes, going over this information here, as an object is falling down, the potential energy and the kinetic energy are basically switching places. So the total amount of potential energy at the top will equal the total amount of kinetic energy it has at the bottom. In other words, the total energy of the system will remain the constant all the way through. Well, in this problem, we just determined that the total energy of the system is going to be always 5,880 joules. That means anywhere along this path, when this diver's going down, the total energy will always be 5,880 joules all the way down. So when they reach the very bottom, the next question is, what is their kinetic energy? Well, the potential energy at the top is equal to the kinetic energy at the bottom. So therefore, real simple, the kinetic energy is going to be equal to 5,880 joules of energy. That's all you had to do for that one. Because the total energy at the top will equal the total amount of energy at the bottom. So this will also be 5,880 joules of energy. Now, for part C is asking how fast is it going? And how fast is it going is dependent upon its kinetic energy. So for part C, this is where we're going to be taking the kinetic energy and converting it into its velocity. So kinetic energy is equal to 1/2 mv squared. And we know what the kinetic energy is. We know what the mass of the person is. The only thing that's unknown is how fast are they going. So what we need to do is we need to rearrange this and solve for velocity. Well, in order to get rid of 1/2, I need to multiply both sides by 2. So I'm going to multiply this side by 2. I'm also going to multiply this side here by 2. This way the 1/2 and the 2 will cancel out. So I'm now left with 2 times the kinetic energy is equal to mv squared. Now I'm trying to solve for v. So the next thing is I need to divide both sides by the mass. So that way the masses will now cancel out. So now v squared is equal to 2 times the kinetic energy divided by the mass. Now, we're trying to solve for velocity, not velocity squared. So to get rid of the square, I need to take the square root of both sides. That way the square root and the square will cancel out. So finally, the formula for the velocity is equal to the square root of 2 times the kinetic energy divided by the mass. So now we have a working equation here. We need to take this and plug in the numbers. So velocity is equal to the square root of 2 times the kinetic energy. Well, the kinetic energy is 5,880 joules. So that's 5,880 joules of energy. Divided by the mass. Now the mass is 60 kilograms. And then we're going to have to take the square root of that. So the way this is going to look on the calculator is going to take 2 times 5,880 joules. I'm going to hit equals. So right now, if I multiply these two, I get 11,760 divided by the mass. So divided by 60, I get 196. Now, the thing is, I still have to take the square root of that. So I'm going to take the square root of my answer here, and I end up with 14, which means the object, for the person, is going to be traveling at 14. Now, if you're trying to find out what's going to happen to the units of this, and you should be able to figure out, well, it's velocity, it should be meters per second, but I just want to show you how this comes about. The unit joules here, one way the unit of joule could be expressed here is a kilogram meters squared per second squared, and it's also being divided by kilograms down here in the bottom. So the kilograms will cancel out. So it leaves you with a meter squared per second squared. But then you still have to take the square root of that. So if you take a meter squared per second squared and take the square root of that, that will then equal a meter per second. And that is your final answer. So when this object, is a 60 kilogram person, jumps off of a board here and drops 10 meters, when it hits the water, you'll be traveling at 14 meters per second. All right, so later on, you'll be doing some example problems very similar to this. So while you're doing these problems here, sometimes it's helpful to draw out the diagram, list all the information that's given to you. And it's also helpful to, if you just remember, potential energy is equal to mgh. Kinetic energy is equal to 1/2 mv squared. And sometimes if you're dealing with the potential energy and kinetic energy, when these two are being transferred, that potential energy can equal kinetic energy. And then also, if you're dealing with the total energy of a system, the total energy is equal to the sum of the potential energy plus the kinetic energy. So these are perhaps going to be the most common formulas that you're going to be using for some of the upcoming example problems. If you have any questions, just let me know.